Multi-category explanatory variables. When are they useful? So let's say that instead of just wanting to compare 2 regression lines, we might want to compare 4 or 8 or 20. So we have some kind of categorical variable. So in the case of corn yields, we looked at comparing 2 different states, Wisconsin and Illinois. What if we want to compare more than just 2 states? What if we wanted to compare Wisconsin, Illinois, Minnesota, and Iowa? Well, we could do that. Another student visited me during office hours, and this was interested in looking at how deforestation changes within a particular region on the map, a pixel. So you could look at a pixel through time, and maybe you see some kind of linear pattern with forest cover change. Or maybe it's not quite linear, but there's some kind of relationship there. Well, in this case, you could have each pixel or each region be a separate category, and you could see, is this relationship in time with forest cover, does it change by pixel or by location? So there's many different applications for this approach. Let's do this example with the simple corn yield case, and we're comparing 4 different states. All right. So, yikes. So we use this when we have more than 2 groups. And we have more than 2 groups. 2 groups for the binary case. This is when we have more than 2. So let's take the example of corn yield. Corn yield in 4 states. Go ahead and pick Wisconsin, Illinois, Minnesota, and Iowa. 4 Midwestern states. So here we'll use the letter M to denote how many levels we have. We have 4 levels. 1, 2, 3, 4. And these are the levels of our categorical variable. Right, so we could say that state is a factor with 4 levels. Okay, so what we're going to do is, let's say, so our response is corn yield, and we have these 4 different states. So this looks a lot like ANOVA, one-way ANOVA, and in fact it is. But we're going to fit it as a regression instead of an ANOVA. So to fit as a regression, we need m minus 1 indicator variables. Let me show you why. So let's say these are our categories, our state, and it has 4 levels: Wisconsin, Minnesota. Oops, I should. I'll keep this order. It's a different order than up here, but I'm going to keep it as I have it. So Wisconsin, Minnesota, Iowa, and Illinois. Illinois is last because it's the least desirable state. Then we have these indicator variables, x1, x2, and x3. We have 3 because m is 4 here. Let me show you how with 3 indicator variables you can uniquely define each level. So for x1, we'll set it equal to 1 for Wisconsin and 0 otherwise. So now we've distinguished Wisconsin from the other 3 states, but now these other 3 states are still that you can't distinguish in them with just x1. So for x2, we'll set that 0 for Wisconsin, 1 for Minnesota, 0 for Iowa, and 0 for Illinois. Now you know that if x1 is 1 and x2 is 0, that's Wisconsin. Okay? You know that if x1 is 0 and x2 is 1, that's Minnesota. But for Iowa and Illinois, those aren't distinguishable yet. So we need one more explanatory variable. And what we'll do is we'll set this explanatory variable to be 1 when it's Iowa, when the state is Iowa. And now you can see that we have 4 rows, and these are 4, each combination here uniquely describes each state. It uniquely identifies each state. So Illinois is when they're all 0, Iowa is when they're all 0 except x3, Minnesota all 0 except x2, Wisconsin all 0 except x1 is a 1. Now I'm just going to note here, this isn't, you don't have to use just zeros and ones for indicator variables, but it's a convenient way to do it. So then let's fit this model, okay? So we've got our x's now. Let's fit the model. Y, this is corn yield, equals beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus epsilon. All right, and our epsilon are independent and identically distributed normally with mean 0 and variance sigma squared, just like we've seen before. So let's think about what this model means and how, when the indicator variables take these particular values, it can reduce down to a simpler model. So what if we have the scenario where we have x1 equals 1, x2 equals 0, and x3 equals 0. Well, what's the expectation for y? So we have beta naught plus beta 1 times 1, right? Because x1 here is a 1, so that would be beta 1. And then x2 is 0 and x3 is 0, so these terms go away. And because we're looking at the expectation of y, the expectation of epsilon is 0, so it's just this here. So the expectation of y, when the indicator variables are like this, x1 is 1, x2 is 0, x3 is 0, this is equal to the mean for Wisconsin, right? Because all the Wisconsin states have this for their indicator variables. So you have your y variable, and then these are the set of x's when it's Wisconsin data. So this beta naught plus beta 1 will be your expected value for the that'll be the expected value for the Wisconsin data, or the mean of corn yield for Wisconsin. Now let's say we have data that comes from Minnesota. So this is Wisconsin. Now in the Minnesota case, we have x1 would be 0, x2 would be 1, and x3 would be 0 for all the Minnesota data. And so the expectation of these y's would be beta naught plus, so beta 1 goes away because it's being multiplied by 0. Beta 2 is included because it's being multiplied by 1. And beta 3 goes away because it's being multiplied by 0. And as before, the epsilons go away because we're dealing with the expectation. And so this would be the mean of Minnesota. For Iowa, we have x1 equals 0, x2 equals 0, and x3 equals 0. Not 0. x3 equals 1. So the expectation of these y's from Iowa would be the intercept plus beta 3. Here, using the same reasoning as before, but it's beta 3 instead of beta 1 or beta 2. So this would be the mean of Iowa. Okay, let's look at the Illinois case. For Illinois, x1 is 0, x2 is 0, and x3 is equal to 0. So for all the observations from Illinois, we set these indicator variables to 0. And so the expectation for the data from Illinois is going to just be the intercept, mu of Illinois. So it's pretty fascinating here. We have set up in the ANOVA case, right? You want to compare, are all of these guys equal to one another, or are some of them not equal to each other? That's the basic kind of test we do in a one-way ANOVA. So this is equivalent to a one-way ANOVA, but we've reparameterized it so that we have this baseline case, and it was arbitrarily decided that Illinois would be this, but where the intercept is the mean for Illinois. So if we estimate the intercept, so beta naught hat, that would be our estimate for Illinois, mu Illinois hat, okay? And then what's nice is that beta 3 is the difference between Illinois and Iowa, because Illinois is beta naught, right? So beta 3 is the difference between Illinois and Iowa. So what would beta 2 be? Well, if beta naught is the mean for Illinois, then beta 2, and beta naught plus beta 2 is the mean for Minnesota, then beta 2 is the difference between the mean for Minnesota and Illinois. And similarly, beta 1 is the difference between the mean for Wisconsin and the mean for Illinois. So imagine if we test these hypotheses, right? What if we test this hypothesis that beta 1, beta 2, and beta 3 are all equal to 0 given the intercept, beta naught. If all three of these are equal to 0, this reduces to testing mu Illinois equal to mu Iowa equal to mu Minnesota equal to mu Wisconsin. Just like we saw in one-way ANOVA. Now, what's a nice thing about setting it up as a regression, not only can you do this overall test, but you can test different hypotheses that are more specific. For example, you could test, what about just beta 3 equal to 0, given the intercept, beta 1, and beta 2. That is, if beta 3 is 0, and beta 3 is the difference between Iowa and Illinois, we can test, is there a difference between the mean corn yield in Iowa and the mean corn yield in Illinois? So that's what this particular hypothesis is doing. It's a pairwise test. We could also test things like, is beta 2 equal to beta 3 given beta naught and beta 1? So this is saying, is beta 2 equal to beta 3? So this is saying, is, let's see here, is the difference between, you can think about it in two ways. One is the difference between Minnesota and Illinois the same as the difference between Iowa and Illinois, right? Beta 2 and beta 3 equal, then the differences between Minnesota and Illinois and Iowa and Illinois will be the same. Or another way of putting that is the mean between the mean of Minnesota and the mean of Iowa the same? Okay, so do Minnesota and Iowa have the same mean corn yield? So we can use our additional sums of squares test to test quite a variety of interesting hypotheses. So again, this is the same as a one-way ANOVA, but it's recasting it in a slightly different way.